Okay, this video is on the ideal gas law. The ideal gas law is, like it says right here, an equality for the four variables involved in Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law to be written as one thing, which would be PV equals nRT. And the main thing I want you to get out of this is this law is this in this equation is what you're going to use when there is no change. Okay, if there is no change in the situation, okay, like example with our, if I have a balloon and I want to know how many, how many moles are in that balloon, or if I wanted to know what the temperature inside that balloon is, or the volume of that balloon, or the pressure of that balloon, okay, I can solve for that using the gas constant, which we'll talk about here in a minute, but also knowing the other three variables, I can solve for the fourth. But there is no change going on in the system. With the combined gas law, you change pressure to see what happens to volume, or you changed number of moles to see what happens to temperature. Here, with the ideal gas law, there is no change going on. It's just a stagnant system, and then you're given four of these five variables, and you're just solving for the fifth. Okay? The Okay, you guys kind of read this already with ideal gases, but ideal gases, they behave described to the ideal gas equation, mainly that there's no volume. Okay, these gases don't have volume. These gases do not collide with each other. But understand that there's no ideal gas. Every gas is a real gas. The ideal gas is just kind of like the perfect situation, the perfect world scenario where if we can identify what a perfect gas would do, then maybe we can kind of get an idea of what a real gas would do. It says right here, real gases behave more like ideal gases as pressure is going to approach zero. But like I said, in that situation, having the pressure approach zero um, is not a very easy task to accomplish. So first thing I want you to do is go ahead and pause this video, write down what P equals, V equals, N equals, R equals, and T equals if I rearrange this equation. Okay, so go ahead and pause the video and do that. And this is what you should end up. P equals nRT over V, V equals nRT over P, N equals PV over RT, R equals PV over NT, T equals PV over NR. Okay, now probably wondering, what is this guy? Okay, well, like I said, he's the gas constant. And we'll take a look at him right now. So R is a constant, so you're going to always want to have the same number. How about this? With a constant, there's a unit. Okay, and the unit that we're going to be using, you want to always have the numbers, or at least the units in the problem, to equal that unit. And we'll go ahead and work out this problem right here so you can see what that unit is. So using STP conditions, which is 273 Kelvin and 1.00 atmospheres, okay, using those conditions and the ideal molar volume of a gas, which is, if I take any gas, 1 mole of it is 22.4 liters if it's at STP. If it's at STP and there's 1 mole there, it's taking up 22.4 liters. So let's go ahead and rearrange the PV equals nRT, PV equals nRT, so I can solve for R, which means it would be R equals PV over NT. And when I plug in these numbers, because this is my pressure right here, this is my volume right here, this is my number of moles right here, and this is my temperature. If I keep all my sig figs, my answer is going to be 0.0821. Okay, that's the number, and this is a very important number, and you're always going to want to know that because I'm not going to put it on the test for you. 0.0821 is the number. Your unit is liters times atmosphere over mole Kelvin. I know, it's kind of a big unit, but believe me, when we start doing problems, you want to have these units so they'll cancel out, and you can see how they cancel out in the next slide. Okay, so let's go ahead and do an example problem. What would the temperature in Kelvin be of an ideal gas if 0.556 mole sample occupied 2,630 milliliters at a pressure of 6.99 atmospheres. So the first thing I want to do is make sure, okay, liter, atmosphere, mole, Kelvin. I want to make sure all four of these units are somewhere in this problem. If they are, then I can use 0.0821. I can use that number. If I can't use that number, then I have to recalculate R, and I don't want to do that. Okay, so we want R to be equal to this number right here, which means we need to have liters in the problem, atmospheres, mole, and Kelvin. So taking a look, what would the temperature be in Kelvin? So I'm solving for Kelvin, so I don't need to worry about that quite yet. I have moles, that's a check. Occupy a volume of 2,630 milliliters, but that's not what I want. So I'm going to convert it through dimensional analysis, and I'm going to get 2.630 liters. Make sure you keep your sig figs. And then a pressure of 6.99 atm. Check. So I have liters right here. I have atmospheres right here. I have moles right here. And I'm solving for Kelvin. So let's go and set it up. PV equals nRT. I'm solving for temperature. So temperature is going to be equal to PV over nR, which means my pressure, which is 6.99 atmospheres, times my volume, which is 2.630 liters, all over N, which is 0.556 moles, times the gas constant, 0.0821. Now here's the thing, liters, atmosphere, mole, Kelvin. I need to include that in my, that whole unit in my equation. So now, I'm going to cancel units out. If you look here, moles are going to cancel out, liters are going to cancel out, and ATM is going to cancel out, which means all I have left is Kelvin, which is good because that's what I'm trying to solve for. So I'm going to go ahead and do my calculations. Okay, 6.99 times 2.630 with 3 sig figs is going to be 18.4. I have 3 sig figs because 6.99 has 3 sig figs. And then my denominator, 0.556 times 0.0821 Kelvin, is going to be equal to 0.0456 with 3 sig figs because both those numbers have 3 sig figs. I do my final calculation, 18.4 divided by 0.0456. My final answer will have 3 sig figs, and it would be 403.5 Kelvin, but I need 3 sig figs, so my final answer is going to be 404 Kelvin. Okay, so that's just one example. Worksheet 1 has 5 more problems. Okay, now, like, the nice thing to do with any equation is go ahead and plug it back in. So you take this temperature right here, this 404, and then go ahead and plug it into R equals PV over NT, right? And go ahead and use this volume unit, use this N unit, use this T unit, and use this P unit. So when you plug in all those numbers, it should equal a number close to this. Okay, there are sig figs, and so there's rounding going on, so it may not be exactly 0.0821, but it should be within plus or minus 100th. Okay, so anywhere from 0.07 something to 0.09 something. Okay, anything more than that, I'm giving you some pretty funky numbers, and I'll make sure I do better. But your answer, if you plug it back in, should be somewhere around 0.0821. What would that be? Liters, atmosphere over mole Kelvin. Okay? So if you guys have any questions, please ask.